Okay, welcome everyone to our video on electronegativity. The learning goals for this video, we will first learn how to determine the electronegativity for each element, and then we'll use that electronegativity value to predict the bonding type of a pair of atoms. So what is electronegativity? Well, electronegativity is a measure of an atom's ability to attract the pair of electrons in a bond to itself. Now, the technical definition talks about a covalent bond, but we will see that we're using it as well to predict when we might likely have an ionic bond. And so electronegativity is the most useful measure to predict the type of bond which will form. Now, in previous science classes, you have learned that ionic bonding occurs between metals and nonmetals. Covalent bonding occurs between nonmetals. And that is generally true. However, the reason behind that has to do with those elements' electronegativities. And we will see in this course that there are lots of examples where we would actually predict a covalent bond, and we can have a covalent bond between a metal and a nonmetal. So here is a periodic table from ptable.com. It's a great website. If you haven't looked at it before, you can look at all sorts of different properties. So this is the image captured from ptable.com, where the values you see below the element names are the electronegativity values. It's color coded. The darker the color, the higher the electronegativity. So we see this general trend going from francium towards fluorine, that the electronegativity is increasing, or moving to the right within a period, electronegativity increases, and moving down within a group, electronegativity decreases. And if an electronegativity is a measure of an atom's ability to attract electrons when bonding, maybe you can think back from last unit, and using our knowledge of periodic trends, can you try to think about why that might be the case? Why do we see these two trends in electronegativity? Something to think about that we'll talk about throughout this unit. So you'll see that we have the values here. Fluorine is the highest, and everything is kind of based off of fluorine. Most periodic tables that you'll see in your textbook, the ones that I have posted on the website, have electronegativity values, and sometimes you might see some small differences, and that's because electronegativity values change over time. Sometimes you might see carbon at 2.54, sometimes 2.55. Hydrogen has changed slightly depending on the addition of the periodic table. And what we'll do to accommodate that is that regardless of the periodic table that you're using, we will always round these electronegativity values to one decimal place. And I'll mention that a few times to emphasize that's what we'll do to standardize our electronegativity values. So if we want to talk about what type of bond is going to form, a helpful way to do that is to look at the difference in electronegativity. If one atom has a very strong attraction for electrons and another one has a weak attraction, that will tell us one type of bond is going to form. But let's start off at the other end of things, where we have equal sharing of electrons. So if two atoms both have fairly high electronegativities, which means they have strong attractions for electrons, and that the difference between their two electronegativities, and so that's this symbol here. Delta means difference. En will stand for electronegativity. So if the difference in electronegativity is less than 0.4, then the electrons within that covalent bond are pretty much shared equally between those atoms. And we call this type of bond a nonpolar covalent bond, equal sharing of electrons. So here is our representation, and we see the black dots here are the two nuclei, and this blue area represents the electron cloud of the bonding electrons. And you can see that in this image, it is totally symmetrical. It might be helpful to go back and compare this image to the one that we'll see on the next slide. So if we have a slightly larger difference in electronegativity, and specifically when that difference is somewhere in between 0.4 and 1.7, then one element has a stronger pull on the electrons. It pulls them closer to its nucleus. However, the other element still has a fairly strong pull, and that means that we're still going to get sharing of electrons. However, it's unequal sharing. A great analogy for electronegativity and bond type is a tug of war. If we think of a nonpolar covalent bond as two people in a tug of war that have equal strength, and so neither of them can pull the rope closer to themselves. In a polar covalent bond, you have one person who's slightly stronger. It's pulling that rope closer to them, but they just can't win. The other one's still got a strong grasp on it. So here's a representation of a polar covalent bond. We have our two nuclei, those black dots, and the electron cloud. We see that one side is much larger than the other side, and that's representing the electrons spending more of their time being closer to the one nuclei. What happens, and this is going to become very important as we move through chemistry, that when one atom has a stronger pull on the electrons, that negatively charged electrons is pulled closer to that atom. And as a result, the atom with the higher electronegativity gets a partial negative charge. And partial charges are referred to as dipoles. So the atom which gains more of that electron, is gaining control more of that electron, gains a negative dipole. The atom with the lower electronegativity gains a partial positive charge, a positive dipole. And dipoles are represented with the delta symbol. So here is a delta negative symbol. That represents a negative dipole. And the delta positive on the other side of the bond is partially positive. So just remember, electrons negatively charged, so the atom which has a higher electronegativity gains a negative dipole. And if one side's becoming more negative, the other side has to become more positive because it's lost some of that electron. Now finally, let's just briefly touch upon ionic bonds. And this one's simple. If the difference in electronegativity gets too great, one atom, the more electronegative atom, can simply take that electron from the less electronegative atom. And the level that we'll use is a difference in 1.7. At that point, electron is transferred from the less electronegative to the more electronegative atom, and we end up with two charged particles, ions. There's no sharing of electrons, and they are attracted to each other now by electrostatic forces of attraction, which we call ionic bonds. So on your worksheet, you'll see a blank chart, which we'll use for three examples, one of a nonpolar, one of a polar, and one of an ionic bond. So we'll flip over to the whiteboard now, and you can fill out that chart as I go through those examples. So here are the three examples that we'll look at. let's start off with the first one at the top here, a oxygen-chlorine bond. So our first step is to get the electronegativity values. And so oxygen, we see the electronegativity value here, and it's 3.44. Now, depending on the periodic table, you might get slightly different values, and some will give it to 1 decimal place, some to 2. The values change over time. So in order to standardize this, we will always round the electronegativity values to 1 decimal place. So for oxygen here, we have its electronegativity as 3.4, chlorine, an electronegativity of 3.2, subtract the 2, 0.2. So a small difference in electronegativity, less than 0.4, which means the difference is so small that they essentially share those electrons equally, and therefore we'd have a non-polar bond. Here's our next example, fluorine. So fluorine has the highest electronegativity, rounded to 4.0. Sulfur, rounded to 2.6. Subtract the 2, and we get a difference in electronegativity of 1.4. So that's in that range where they don't share them equally. Fluorine is pulling the electrons closer to its nucleus, but sulfur still has a fairly strong hold on those electrons. So they are still sharing them, just unequal sharing, which is a polar bond. In our final example here, we have calcium with an electronegativity of 1.0, and bromine has an electronegativity rounded up to 3.0. And remember, always just subtract the smaller value from the larger value. And we have a difference of 2.0. So if the electronegativity difference is greater than 1.7, it means that the more electronegative element has such a strong pull that it takes that electron, can take that electron away from the less electronegative or more electropositive element. And we end up creating ions because one atom has gained an electron and one has lost one. And when ions attract each other, we have ionic bonds.